All right, let's take a look at our lesson for today. We are in a new unit, yay. This is a unit of derivatives for analytical applications of the derivative is what we're going to be working on in this unit. And the first lesson is a new theorem. I know we can't wait. We love our theorems. I know. This is called the mean value theorem. So the first thing I want to do, I want to talk about the mean value theorem. We're going to go through some, criteria. In order to use the mean value theorem, you have to have two things that are true. F, the function, has to be continuous on the closed interval. Okay, that has to be true. The second thing that has to be true is f has to be differentiable on the open interval. So those are criterias for being able to use the mean value theorem. So if those things are true, then we know how theorems go, right? It's the if kind of then statement. If you have these criteria true, then there exists a number c. Okay, this number c is an x value. Then there exists a number c between a and b. So a and b is the interval that we were given right here. Whatever those numbers were, that's what we're looking for. Then there exists a number c, which is an x value between a and b, such that the first derivative at c is going to be equal to the average rate of change between a and b. Now, that's a lot of math words. I know, it's a lot of math words. So what I'm going to do is I want to get over here and draw a picture. I want to draw a picture of really what it is we're talking about. So let's say I have a function right here. We're just going to call this a and this b. Okay, so let's say we start here and, we go to here. Okay, so that function is, and let me just make this a little bit more. Come on, little thing. There we go. Let's make it a little bit more obvious. Okay, so what this is saying is that this average rate of change, and I'm going to highlight this average rate of change is the pink one, right? So average rate of change would be this slope right here, the slope of this line. Okay, this slope right here would be the average rate of change. And what they're saying is that average rate of change slope is going to be the exact same as the derivative at least once, the derivative of f. So we know, how can we, off of a graph, how would we read the derivative of f? What would that look like? That would be the slope of the tangent line, right? That's what that is. The derivative at c, whatever c is, the c is going to be somewhere between, c is going to be somewhere inside this interval between a and b. There's going to be some c inside of there. And that's it saying the slope of the tangent is going to be equal to the average rate of change. Well, what would that visually look like? So if we could kind of think about it, how many places could I draw a tangent line that would be parallel to the average rate of change? We want the slopes to be the same, right? So you could probably see like that location would be pretty good. Right? Of course, my drawing isn't that great, but there's probably somewhere right around here. That would probably be a C value, right? That probably looks good. Is there another place you see that might be? What about this spot right here? That's looking pretty good. Okay, so this would be like another C value. Now we're only guaranteed one. We're only guaranteed one, but sometimes we get more than one. Are there any more, do you think? We have a few more, don't we? Like this spot right here, that would be a good spot right here. That'd be another one. And then I have one more. So I actually do a crazy one. This crazy one had 4 different C's that would meet this criteria. So this is a visual representation of what this formula guarantees us. Now, the important thing to remember is that this part right here, this average rate of change, is between the endpoints. The endpoints matter. That is between the endpoints. And the value of the derivative is between, is inside of this interval, somewhere between a and b. All right, so questions on the theorem itself. Okay, so we talked about it in words. So yes, it's going to be on a formula quiz. It's a 3. So number 1, you would write f is continuous on the closed interval. Does this sound familiar to anything? IVT, it's very close to IVT, isn't it? IVT doesn't ask for differentiable, but MVT does. So bringing that up, I do want to talk about the difference between MVT and IVT because they are sometimes confused. So I have this little box right here where we're going to kind of dig in there and see what is the difference. How do I know which one to use? Because like I said, these are usually the most confused ones. Some people use one versus the other incorrectly. So let's talk about it. First, let's go to our old favorite, the IVT. What did we use IVT for? We used IVT to show, we basically said, okay, every y value exists between the two y values at least once in the interval. So let's remind ourselves, what were the criteria for IVT? We've got this memorized, right? What needed to be true? F is continuous. It's continuous from A to B, okay? And number 2, it's continuous. What else had to be true? Very nice. F of A cannot equal F of B. So the y values of the endpoints cannot be the same. Do we remember there's 3 criteria for this one? Very good. K is between, now K is a y value, so it's between F of A and F of B. And what was our conclusion? Therefore, and it was like this, there must be a C. They like that letter C, don't they? There must be a C between A and B for which F of C equals K. And K is that y value, right? K is the y value. So that was our IVT. What it was doing is it was taking a function and just in and of itself, just like the position. It's taking the position, it's saying, okay, I've got a position. I want to make sure this y value is, can I get to this y value? That's what IVT is about. It's about like one level of a function, like either the position by itself or either the velocity by itself. It's not comparing, position and velocity. You with me? It's one function. MVT branches out from just comparing, a function with itself. It's comparing the derivative. It's comparing the derivative with the average rate of change. That's what it's doing. So it has to mention something about a derivative and average rate of change to use MVT. And we just went through those criteria for MVT where you would, right, it's continuous on the closed interval, differentiable in the open. Then you have this lovely thing going on right here. Then this will be true. Then f prime of c is going to be equal to f of b minus f of a over b minus a. Okay, so that's the difference between mean value theorem. Here, mean value theorem, we're focusing on the derivative and the average rate of change. Here, we're just focusing on a y value. Just a y value inside of one function. Okay, does that make sense? Okay. So I have a couple of examples that we want to go through. And I do have, now on number 1, we don't need a calculator, but I really would like to use the calculator to be sure that we're still up with our calculator skills on what would we do if we were to do this in a calculator. So we're going to use a calculator just to practice that. All right, so number 1, use that function to answer the following. On the interval 2 to 6, what is the average rate of change? Okay, so that's a formula that we know, right? That formula that we know. And in this case, it's going to be f of 6 minus f of 2 over 6 minus 2. Now, what I'm going to do is I'm going to go in my calculator and make my calculator do that. If I didn't have a calculator, I'll just write it out. I'll use a calculator, but if I didn't have a calculator, what I would do is I would put 6 everywhere the x is, right? minus, and then I'm going to put 2 everywhere the x is. And then I'm going to go over 6 minus 2. Okay, that's what I would do without a calculator. And I would just do the arithmetic, you know, in my head or on paper or something. But what I would like to do is practice. We want to kind of practice with the calculator and make sure that we can do that with the calculator. So I'm going to pull this up. Are we all okay with that? Okay, and I don't have this function written anywhere, so I probably have to have you all help me, tell me what that is. So I want to put this in a grapher so I can store it. So what was that? Was it negative x squared? Is that right? And then what was it?
Plus 3x plus 10.
Thank you. Plus 3x. Was it plus 10?
Yes.
Okay, thank you very much. So I'm just storing it here. I'm just holding it there. There it is. All right, so now I'm going to insert a page. I'm going to do a calculator page. And here I'm going to actually write the formula for average rate of change. I'm going to do control divide, right? No, we want control divide, my little friend. Okay, control divide. There we go. So I want this to say like f of b, right? I've got it stored right here. F of, and it was 6, right? F of 6 minus, and then f of 2 over 6 minus 2. This VAR, this little thing has my functions stored, and if I had more than one function stored here, it would just list them, F1, F2, F3, but I only have one stored there. So the great thing about this is you see how much work that would have been, plugging the 6 in and plugging the 2 in and then doing all that arithmetic, and then now this is all I have to do, and it gives me my answer. That's quite handy. I want to make sure that we all know how to do that, because you will be faced having to do that on a test at some point. Right, where we would need to, where it would just be easier for you if you were to store the function in your grapher and use it like this. Does that make sense? Okay, so my average rate of change is -5. So let's go back. And so this turns out to be -5. And did we have units? We don't have any units, do we? So yeah, I don't see units. So we're just going to say average, we're just answering the question, rate of change. They love it when you give their words back. Average rate of change is -5. Okay. So what did we just do? We just, I'll just look at the graph real quick. So if we look at this graph, we're basically looking at between two, like the y value here, we are connecting between 2 and 6, 2, 3, 4, 5, 6. So we're like connecting these y values with a line, right? This is our slope of our secant line. That's what we calculate. The slope of the secant line is -5. Now they want to know on the interval, when does the instantaneous rate of change equal the average rate of change? Okay, that's the formula. We should, even though it's not saying that this is MVT, we really should recognize that this is MVT. Right, because they're saying average rate of change equals instantaneous rate of change. That's MVT. So when would that happen? Well, how are we going to do that? Well, we know what the average rate of change is. How do we know when the instantaneous rate of change is -5? How do we know that? Well, we would need to find an equation for instantaneous rate of change, right? And how do we do that? We just take the derivative with me. So we do f prime. So f prime of x, so that would be what, -2x plus 3. Okay, so we want our instantaneous rate of change, which is -2x plus 3, to equal the average rate of change. So let's make that happen. Let's set that equal to each other. So we want the instantaneous rate of change, which is -2x plus 3, equal to the average rate of change. And then we want to figure out, what would x be? That's my question. What would x be? That's what they want to know. What would it be if the derivative were equal to the average rate of change? So I'm simply going to solve for x. I would move my 3 over, and then I would divide by -2, and I would get 4. So we're going to answer the question. So what would X, so when does instantaneous rate of change, so instantaneous rate of change, again, we're just giving them the words back. Instantaneous rate of change equals average rate of change at x equals 4. That's answering their question, and the proof is in the work that we just showed. Okay? So that's using mean value theorem in one type of way. Are we okay with that? Okay. So let's look at, we have just one more question.
Can you stay on that for a second?
Sure. So they really like it when we are specific with our answers and we repeat back like the question to make sure we've answered what they've asked. Does that make sense? So it's very clear what our answer is. It's 4 because the instantaneous rate of change equals the average rate of change at x equals 4. Okay? All right, so let's look at this last question. So we've got a hot air balloon is launched into the air with a human pilot. The twice differentiable function h models the balloon's height, measured in feet at time t, measured in inches. Okay, so this is a height, right? This is a position. So this is a position information. Every time you're given information, I would highly recommend that you write down what kind it is, just as a clue, like a trigger for you. That's a position. Those are position numbers. For 5 to 15, must there be a time t? These words right here should scream to you theorem. Must there be a time t? That should scream theorem. I mean, now I don't know which theorem it is yet. We're going to figure it out, but those words mean use a theorem. They don't just mean make up stuff. Must there be a time t when the balloon is 50 feet in the air? What kind of information is this? This is position information, right? 50 feet is a position. So if we have position data and we want to know about a position, do you think the theorem is going to be IVT or MVT, intermediate value theorem or mean value theorem? It's intermediate value theorem, right? Because intermediate value theorem is dealing with one function. One function. Let's look at that again. Intermediate value theorem is dealing with just y values of one function. It is not comparing derivatives and average rates of change. That's all it's doing. It's using the y values of one function. What's mean value theorem doing? It's comparing the derivative and the average rate of change. Okay, that's a way more complicated thing to do than just dealing with the y values of a function. You with me? Okay, so when we look at this question again, I just want to ask again. So we know it's a theorem. We know we have two choices, intermediate value theorem or mean value theorem. We have position data and we want to verify something about the position. Which theorem am I going to use? Intermediate value theorem. That's the theorem I'm going to use. Okay? So let's go through, and it says justify. Even if it didn't, we would need to justify. So let's go through our theorem. We just went through it before. So number 1, we would say H is continuous. And we want to use what they use. Don't go 0 to 30. Just use what they use. They just want to know about 5 to 15. So we're just going to say it's continuous, 5 to 15. Check. So what else do we need for IVT? We need it to be continuous. We need the y values not to be the same, right? So we need h of 5 cannot equal h of 15. And I need to actually verify that. H of 5 is 40. 40 does not equal h of 15 is 70. I need to write those down. I would write them both down if I were you, just to cover all your bases. Okay, those y values are not the same. Okay, step 3. What was our step 3? K. What's K? It's the y value. It's the y value. It's this. 50 is K, right? That's the y value. So we have to say 50 is between, not 50 is between 5 and 15, because 50 is a y value. 50 is between the y values at 5 and 15. 50 is between 40 and 70. Now, some students prefer to write like 40 less than 50 less than 70. That is perfectly fine if you write it like that, if you want to put it in an inequality.
Never mind. I was going to ask, how did you know to use 5 and 15, but I just saw it.
Oh God, yes, right here. That they are really, they will really tell us. They are not going to let us decide. Okay, so those are our 3 criteria. So now that those are true, we can verify. So therefore, there must be a time C. There must be a time C between 5. Notice I'm not saying between A and B. I'm saying between 5 and 15. You should put numbers on that. Please don't leave it as A and B in your context, or you'll lose points. Between 5 and 15, such that f, and now we're not going to say f, we're going to say h. The function is h of c equals, and what was our y value? 50. H of c equals 50. And we have just completed what they've asked by using, and you can say, by intermediate value theorem. And abbreviating IVT is acceptable. But to be honest, you don't even have to name it. If you have all these criteria written, that is good enough. You do not have to name it. Okay? All right. The last part of this question. For 20 to 30, must there be a time t? Okay, here we go again with the must there be a time t. This should scream to you. This should scream theorem. This is a theorem. Must there be a time t? That is talking about a theorem. When the balloon's velocity is 1.5. This isn't talking about the actual position or height. It's talking about velocity. So what should we look at using, IVT or MVT? MVT, because it's talking about a derivative, not the position. Okay, and let's think about what's the deal with MVT? Let's go through the criteria. So to make sure we can use it. So number 1, H is continuous. And we need to use what they use, 20 to 30. Number 2, they want to know that H is differentiable. Now, we're going to have to look to see differentiable on the open interval, 20 to 30. And this is why I know. I want you to notice these words right here. The twice differentiable function h. This is how I know. That's how I know that h is differentiable, because it told me in the prompt. H is differentiable. I can't just make that up. That's typically why they put that in the prompt, is to tell us, oh yeah, it's differentiable. Okay, so we can use mean value theorem, but what's the deal with the 1.5? I mean, I need to figure out where that comes from. But I need this slope of the secant needs to equal the derivative somewhere. So I'm going to have to find the slope of the secant between 20 and 30. That's what I need to find. So we're going to do h of 30 minus h of 20 over 30 minus 20. We're finding our average rate of change, because that's what mean value theorem does. It compares average rate of change to a derivative. This value right here is an instantaneous, this is instantaneous rate of change. That's how I know. So you'd be like, well, how do you know you're supposed to find the average rate of change? Well, because they gave me the instantaneous rate of change, and I need to find the average rate of change to see if they're the same thing. That's a typical thing they're going to ask us to do. So let's take the data out of the chart. So h of 30, let's see, is 80 minus h of 20 is 65 over 30 minus 20 is 10. So what is that? 80 minus 65, what is that, 15? 15 over 10, which, we'll look at there, that's 1.5. So that we're building our case. We've got our case built. So now we can say that, therefore, there must be a time t. Therefore, there must, gosh, I can't write. There must be a time t between 20 and 30 for which h of 30 minus h of 20 over 30 minus 20 equals 1.5. And there's our MVT.